Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the alkylation of benzene. We're going to talk about what the alkylation of benzene actually is, outline the steps in the mechanism for the reaction, and look at why a halogen carrier catalyst is needed. The structure of benzene and other reactions of benzene, including acylation, are outlined in separate videos. Check the links in the description below. Before we talk in detail about the alkylation of benzene, there are a few essential ideas you need to be comfortable with. Benzene is a cyclic hydrocarbon with a delocalized electron system that reacts with strong electrophiles in electrophilic substitution reactions. It is essential you are comfortable with this general mechanism in order to follow the rest of the video. If unsure, please check the link in the description below for the video that outlines this in more detail. Electrophiles are electron pair acceptors. They are usually positively charged and are attracted to areas of high electron density. A substitution reaction is where one group or atom in a molecule is swapped for another group. Chloroalkanes are compounds that have a functional group consisting of a carbon atom that is bonded to a chlorine atom. Chlorine is highly electronegative and so pulls electron density away from the carbon atom towards itself, leaving the carbon with a partial positive charge. This all makes the carbon-chlorine bond weak, and as a result, if given a little nudge, it can be forced to break, leaving a positively charged carbon atom behind, creating what we call an alkyl ion. An alkyl group just refers to a carbon chain bonded to another carbon chain. So, recap done, let's go. When benzene undergoes an alkylation reaction, an alkyl group, usually from chloroalkane, is swapped or substituted for a hydrogen bonded to a carbon atom. An alkyl group gets added to the benzene ring. This is a really useful reaction in organic chemistry as it allows us to form a carbon-carbon bond, something really rather special in synthesis reactions. The type of mechanism occurring is electrophilic substitution and follows a standard mechanism. This particular mechanism pathway was discovered in the 19th century by two chemists called Friedel and Crafts. As a result, it is referred to as a Friedel-Crafts alkylation. The acylation of benzene follows a virtually identical pathway and is also considered a Friedel-Crafts reaction. That reaction has been covered in a different video. Check the link in the description below. At this level, I think it's probably easier for you to just refer to the two reactions as alkylation and acylation rather than Friedel-Crafts, just to make sure you got them completely separate in your head. An alkyl group just refers to a carbon chain, and chloroalkanes are a great source of alkyl groups in organic chemistry. And, as mentioned in the recap, can quite easily be nudged into forming alkyl ions that can act as electrophiles. To give this nudge and weaken the carbon-chlorine bond to the point of breaking, a catalyst is used. The carbon-chlorine bond in a chloroalkane is already highly polar, as the chlorine pulls electron density towards itself. Because the carbon has a low electronegativity, it doesn't put up much of a fight and ends up being partially positively charged. To get the carbon-chlorine bond to the point of breaking, a halogen carrier is used. A halogen carrier basically just means a metal, usually iron or aluminium, that is bonded to atoms of the halogen in question, in this case chlorine. Aluminium trichloride will be used in this example, although you may also see iron trichloride being used. A lone pair of electrons on the partially negative chlorine in the chloroalkane get attracted to the metal in the halogen carrier and tries to form a coordinate bond. Note it's a coordinate bond as both the electrons are coming from one atom, the chlorine. This means the chlorine atom has lost some of its electron density. To try and get it back from somewhere, it pulls the electrons in the carbon-chlorine bond towards itself even more, creating a much larger polarity and significantly weakening the carbon-chlorine bond to the point of breaking, effectively forming an alkyl ion with a carbon that has a positive charge. This carbon atom is now sufficiently electron deficient to act as an electrophile and is able to react to benzene. The reaction with benzene now just proceeds as expected, electrophilic substitution. To get the reaction started, a little bit of heat is needed. A pair of electrons from the delocalized ring of electrons in benzene is used to form a bond between a carbon atom in the ring to the positive carbon atom in the alkyl ion. This breaks open the ring of delocalized electrons and forms an unstable intermediate. To reform a full ring and get back some stability, the carbon-hydrogen bond on the same carbon as the carbon-alkyl group breaks. This electron pair is put back into the delocalized system and a H+ ion is removed by a chlorine atom from the halogen carrier intermediate just formed. This leads to the formation of an alkyl substituted benzene ring, HCl, and the reforming of the original halogen carrier, aluminium trichloride. This is why the halogen carrier is considered to be acting as a catalyst, as it gets reformed at the end of the reaction. So, to summarize, benzene reacts with chloroalkanes in the presence of a halogen carrier catalyst to form alkyl substituted benzene. The reaction is an example of electrophilic substitution, and a halogen carrier catalyst is needed to help create the alkyl ion to start the reaction. This specific type of electrophilic substitution is referred to as a Friedel-Crafts alkylation. I hope you found this video useful. Please check out other relevant videos in the links given below and visit chemistrystudent.com for free notes and revision materials.